In this video we will see the demonstration program of how do we implement a binary tree. Now it's a binary tree, it's not a binary search tree. This demonstration program will help us to understand why binary trees are not preferred and why the binary search trees are preferred over there. Now let's write the program. We know that the structure definition of the binary tree, yesterday we have seen it. How do we write it? We say struct node, and this node has three things. What are the three things we have? Struct node star left. Next we have data. Now this data can be of any data type, and for simplicity I take it as integer data type. And the next thing what we have over here is struct node star right. Right, this is the structure definition of a node of a binary tree. Why? Because we have left child and right child along with the data. That I have said it in the previous video, please refer to that. And then we say main. Now this binary tree is represented by what? It is represented by root. And what is the value of root? The value of root to begin with is null. If the value of root is null, that means it is an empty binary tree. Hence, what do we write over here? We say struct node star root is equal to null. As we have said, struct node star head in case of linked list, where linked list was represented by head pointer. Here the tree is represented by what? The root of the tree. And if the value of root is null, that means it is an empty tree. Right. Now what we do, we will create a node. Now to create a node, we will write one function called as getNode. We know already how to be. Let us now write the function getNode. Now how do we write the function getNode? We say struct node star getNode, because after it creates the node, it will give the address of that node. And we will take one parameter as integer, right? That means what? It will populate the data. That integer is not standard, but to reduce the code, I have written it that. Now, what is the first thing for us? We have to create the node. How do we create? We say struct node star p. P is equal to struct node star malloc of size of struct node, right? And what do I write over here? I say p arrow data is equal to e, and we say return p. Now what will happen? I will explain. Struct node star p star root equal to null. That means a memory is created. It is root. And what is the value of this root? Null. Let the address of this be say 0x1000. Okay. Now initially the tree is empty. I want to create a node. And how do we say it? We say getNode. And what does this getNode function takes? It needs an integer. Let us give that integer as 10. Now what will happen whenever you call the function getNode? The scope of the getNode gets activated. Okay. Now the first thing is it says struct node star p. Okay. Assume that this is struct node star p. This p is the node that is created. And let the address of this be say 23,000. Okay, p is equal to struct node star malloc and all. P arrow data. Now this node has three things over here. What are the three things? Left, data, right. Now let this be left, this be data, and this be right. And what is the next thing? P arrow data is equal to e. What is the value of e that we have said? 10. Therefore 10 is being written over here. And what should be the left and right to begin with? Left and right to begin with is null. Therefore before I say return p, what I have to write over here? I have to say p arrow left is equal to null and p arrow right is equal to null. Therefore you say p arrow left is null, p arrow right is null. Why we write null over here? Because there are no left child and right child. And whenever there is no left children and right children, we write null. That already have said it. And what do we write over here at the end? We say return p. Now what is the value of p? 23,000. That means 23,000 will be returned over here, and that I need to store it in root. Therefore I say root is equal to, hence the value of root from null changes to what? 23,000, and this becomes the root of the binary tree. Right. Now suppose I want to add one more node over here. Okay. Now how do you create a node? We say get node. and whatever is the data that you want. Suppose the data I want it to be 20. You say P is equal to malloc. Now this is P is equal to malloc. It has three things: left data and right. P arrow data is E, P arrow left is null, and P arrow right is null. Let the address of this be say 24,000. Let the address of this be say 24. Return P. That means it returns 24,000. It has to be stored somewhere. Now this 20 I want it to be as what? Left child of 10. That means here this left pointer should be pointing over here. What left pointer? Root's left pointer. Therefore, what do I write over here? Root arrow left is equal to. Now, what is equal to? Get node. What does it return? 24,000. And what will be stored over here? 24,000. And this link is established. And you see that 20 has become left child of 10. Suppose I want to make 30 as right child of 10. How do you write it again? We say get a node of 30. Now what does it will do? It will create a node. Suppose this is the node that is being created. P arrow data is E, P arrow left is null, P arrow right is null. Suppose the address of this is 25,000. Now this 30 I want it to be as what? Right child of 10. That means here I want to store 25,000. Where I want to store? In root arrow right. Therefore, what do we write over here? We say root arrow right is equal to get node, and what does the get node will return? It will return 25,000. That means it is a physical representation, and this arrow mark is what? A logical representation. Suppose I want another node over here, 40, and 40 I want it to be right child of 20. 40 I want to be as what? Right child of 20. How do we write it? We say get node of 40. Now when I say get node of 40, you say P is equal to malloc. This is P is equal to malloc. Let the address of this be say 26,000. There are three things over here: left data and right. P arrow data is equal to E, that is 40. Left is null and right is null. You say return P, return 26,000. Where you want to store 26,000? Over here. But do we have a pointer for this? We don't have a pointer for this directly. That means I have to traverse through root. I can say root arrow left. I can say what? Root arrow left. Now when I say root arrow left, what is root arrow left? 24,000. In this 24,000, what I am interested in? I am interested in the right pointer. Therefore, I say root arrow left arrow right is, now root arrow left is this complete node, arrow right is this particular thing, is equal to P. That means 26,000 is stored over here. Suppose I want to add one more node, 50 over here, and I want 50 to be right child of 30. I want 50 to be as what? Right child of 30. How do we write it? Right. See over here, we say get node of 50. Now, what does this get node of 50 will do? It will say P is equal to malloc, P arrow data is E, P arrow left is null, and P arrow right is null. Done. Now, I want 50 to be right child of 30. Can I get 30 directly over here? No. I have to say root arrow right. I have to say root arrow right. Now when I say root arrow right, this complete node will be taken, and in this complete node, am I interested in left pointer or data or right pointer? I am interested in right pointer. Therefore, again I have to say over here, arrow right is equal to get node of 50. This is how the nodes will be created, and this is a simple demonstration program of the binary tree. Now, in this binary tree, do you see that the data less than 10 are on LHS, the data greater than 10 are on RHS? No, we don't see, because 20 is greater than 10, but still it is on LHS, right? Therefore, you cannot conclude that it is a binary search tree. Therefore, now what will happen if it is not a binary search tree? Suppose this data might be 8, this data might be 8, this data might be -1, this data might be 7, and this data might be 5. Right, this might be the possibility. Okay, or this data might be 15. This might be the possibility. And if this is the possibility, I want to search 8. Can I conclude that 8 can be only on LHS? No, because there is no ordering of elements saying that all elements less than 10 will be on LHS, all elements greater than 10 will be on RHS, as in binary search tree. If I want to search -1, can I search only on the left subtree? No, it can be on right subtree as well. It means you need to search complete tree. And searching complete tree takes n time. What do you mean by n time? N time means if there are 5 nodes, I want to search for 5 times. If there are 500 nodes, I have to search for 500 times. If there are 5,000 nodes, I have to search for 5,000 times, because I do not know where data is available. Is it on LHS or it is on what? RHS of the subtree. That means it is same as linked list. It is same as what? Linked list. Because in linked list as well, if you write like this, 1, -1 and 0, if I want to search 0, I have to search the complete list because I don't know where it is available. That means if there are 3 nodes, I search for 3 times. If there are 500 nodes, I search for 500 times. That means it is also a n time algorithm. That means we have not achieved anything good over here. Now, if we have not achieved anything good, then why we should use trees over here, and that too with 2 pointers, and that too in hierarchical nature. Right? The search time is very, very long. Now, in order to reduce the search time, we come with the mechanism of what? Binary search tree. That means this is just a demonstration program to say how does the tree work, but this is a normal binary tree. And why we don't prefer normal binary tree? Because the search time is n, and if I write binary search tree, the search time would be log n. How it would be log n? See over here. If I say 10, 5, it is less, right? 2, and this can be 6. This can be 13, 12 and 15. Suppose I want to search 15. At one time, what you do? You neglect half of the nodes. Right? Now, because 15 is greater than 10, you come over here. Now again you compare 13 with 15. 13 is greater than 15. Again you neglect half of the nodes. That means at each step you neglect half of the nodes, and you find the node at the log n time. How it is log n? That is algorithm course. I will explain it later. That means here you are neglecting half of the nodes because you know where 15 might be available. Might be. I am not saying that it is available. Where 15 might be available? On the RHS of 10. Where 15 is available? On the RHS of 13. Do you need to search on LHS? No. That is the advantage of binary search tree. But in a normal binary tree, if I want to search -1, where -1 is available? Is it only available on LHS? No, because there is no ordering of elements. Hence, we prefer binary search tree. Now, let us see how do we write the program for binary search tree.